Hello everyone, my name is Quentin Bramas and I will present a joint work with Anissa, Lamani and Sebastien Tixeuil entitled The Agreement Power of Disagreement. So the model, so we are talking about mobile autonomous robots. So you have a set of robots here represented as points in a plane, and all the robots are anonymous, uniform, which means that they execute the same algorithm, disoriented, which means that they don't have a common notion of coordinate system or chirality. They are silent, which means that they do not communicate explicitly, and they are oblivious, which means that they don't remember past executions, so they don't have persistent memory. So what do? They perform cycles of look, compute, and move. So first they look at their surrounding, and they obtain the positions of the other robots in their own coordinate system. Using only this information, the robot computes a target destination and then moves toward the target along a path. They are not sure to reach the target, so maybe the adversary will stop the robot in the middle, and so the robot will wake up later and start a new cycle looking at the surrounding, computing the destination and moving towards the destination. But the adversary cannot stop the robot before the robot traveled a fixed distance. So if the robot always chooses the same target, we are sure that it will reach the target eventually. So we have several synchronous models. Here I will just present two synchronous models, the fully synchronous model, where at each round every robot executes look, compute, move simultaneously. The semi-synchronous model, we have again a notion of round, but here only a subset of robots execute their cycle each round. So here, for instance, only robot 1 and robot 3 execute their cycle. In the second round, only robot 2 and 3 execute their cycle. And so the robot don't know who will execute the cycle, so maybe they don't know if they will move alone or move together. So one of the most fundamental problems in this model is to see if it's possible to gather all the robots in a single point, not known beforehand. So here the robots must agree on a point and move towards this point. So starting from any configuration, we want to reach a configuration where all the robots occupy the same position. And when there is two robots, we call this problem the rendezvous problem. And so the question is, is it possible, or what if it's not, what are the additional assumptions that we need to make in order to make this problem solvable? So for the related work, it's well known that in semi-synchronous setting, the problem is not solvable without additional assumptions. This was made by Suzuki and Yamashita in the seminal paper in 1999, when they actually defined the model of autonomous mobile robots. So they proved that it's not possible. I will show you the proof, or sketch of the proof just after. Then we actually showed that this year in Algo Sensor 2021, that just agreeing on a single axis is enough to solve the problem in semi-synchronous. This is actually quite surprising, because even with a single axis, two robots may have symmetric views, but still we can solve the problem in this case. And what we'll show in this paper is that if robots disagree on the unit distance, then the problem becomes solvable. So you see that either robots should agree on something, or they should disagree on the unit distance. Also, quickly, in F-sync, we know that the problem is solvable by a simple algorithm, just move to the middle. Since robots execute at the same time the same algorithm, they will move to the middle and reach the middle together. Of course, if they are stopped before by the adversary, they are still coming closer and closer. So at some point, the adversary cannot stop the robots before they reach their target, and so they will move to the middle and gather. So quickly, I will show you the main argument for the impossibility of the rendezvous in the semi-synchronous setting without additional assumption. So assume an algorithm exists, and we can see that there must be a rule in the algorithm saying that a robot must stay idle in a specific view. So if there is no such view, we know that if at every point in time, both robots will move. So if they move to the same point, we just activate one robot. If they move to different points, then we just activate both robots and they will move to different points. There must be a rule saying for a given view to stay idle. And so we can create a new configuration where we put both robots in this view. So R1 will have a view V and R2 will have the same view V. And in this configuration, no robot will move, so they will stay idle infinitely often. And so they will not gather. So now, how do we solve this problem if they have different unit distance? So now, just we'll start by some notation that are important for the remaining of the presentation. So when you have two robots, R1 and R2, so they have different unit distance. Here I represented the unit distance by an arrow pointing at the other robot. And so we'll call unit 1 the unit distance of R1, and unit 2 the unit distance of R2. So we'll assume without loss of generality that unit 1 is greater than unit 2. So the ratio, and we'll denote the ratio of the unit distance by rho. So it's greater than 1. We know that if rho is 1, the problem is unsolvable. And so this implies that both robots will see the distance between them differently. For instance, R1 will see a distance d1 and R2 will see a distance d2. And we have the same relation between d1 and d2 as for unit 1 and unit 2. It's just the converse. So here, for instance, d1 is equal to 2 because you see that you need 2 arrows to reach R2. On the other way, you need 4 arrows to reach R1, starting from R2. So now how do we solve the problem when, for instance, a row equals 2, which is a simple case, and we'll see later how to generalize this assumption. So here we start with the assumption that one distance is 2 times the other distance. So we can define the level of a robot Ri, which is the unique number Li, such that the distance seen by robot Ri is in the interval 2 to the power minus Li and 2 to the power of minus Li plus 1. So actually we partitioned the set of numbers into intervals with the length of the double size, and distance d seen by robot I falls into one of this interval. So for instance here, same as before, but here, so the level of robot 1 is minus 1, because 2 is exactly 2 to the power of minus 1. And here it's for the second robot, the level is minus 2, because 4 is exactly 2 to the power of minus 2. And so we have actually, since the distance of d2 is 2 times the distance of d1, we have that the level of L of the first robot is always 1 plus the level of the second robot. And so we can create an algorithm saying, okay, executed by a robot R, if my level is equal to 0 modulo 2, so if it's even, then I stay idle. If it's odd, then I move to the other. And since one robot has an even level, and the other has an odd level, we don't know which one has which, then one robot will stay idle and the other will move to the other. And so there is a time where the robot that is dictated to move will be activated, and so will move toward the other robot. Okay, so the proof is that one robot will move to the other. If it does not reach its target because the adversary may stop it before, then at least the distance decreases. So at some point, if the distance will be small enough so that the adversary cannot stop the robots during their movement. And so at this point, we will still have only one robot that will move to the other. And so eventually, one robot reach its target. So now, how do we do if rho is not 2, but is in an interval between rho min and rho max, with rho min and rho max arbitrary numbers greater than 1? So here, just to understand how we will generalize, we just look again at what happened when rho equals 2. When rho equals 2, we actually have, so the line is partitioned into segment interval where if I see a distance in this interval, I do not move, and if I see a distance in the other interval, I move. And so you can see that the length of those intervals are doubled every time, or are divided by 2 if I come closer to 0. And if one robot sees the distance in this interval, the other sees its distance with the other robot in this interval. Okay, and so if I move one robot so that it comes closer and stop in the middle, then the distance of both robots will decrease. And if one robot has its distance moving in the interval stationary, then the other robot will have its distance in the move and interval, like this. So we know that for sure both robots are never in the stationary interval. Okay. The problem is that here, okay, so we'll just look at this. If I just use the same interval, but now we don't have the same guarantee about the distance. So here, if R1 sees a distance in this interval, the other robots, we don't know because it's between rho min times the distance here and rho max times the distance here. So it's maybe in the red interval here. So there is a problem if, for instance, R2 sees the distance between the robots in here, and so it will think it will be in the stationary interval. So both robots will be stationary and they will never move. Okay, because it can be anywhere in this interval. And so here it's a problem. So we have to change the intervals here so that both robots cannot be in a stationary interval. So by moving like this, it will be okay. And so how to decide how to construct this interval? Well, look at the extreme cases. If R1 is really close to this boundary here, like at distance A, then B should be A times rho min. Okay, so we have this equation. On the other side, if R1 is almost equal to B, then you see that this boundary, we should have A prime equal B times rho max. Okay, so we have this. And if we apply this for all the interval, we can construct a sequence of intervals like this. So the SI interval are the set of intervals of this form. And you see that it's like to go from one boundary to the other, we just multiply either by rho min or by rho max. And so the intervals look like this. So we have interval where the robot will stay stationary, interval where the robot will move, and so on and so forth. And so these are called the levels of the robots. Okay, so if I look at the distance between me and the other robots, it falls into a single interval, either SI or MI. Okay, and usually the important thing is just either if it's A or M, and either I is even or odd. Okay, so now the important property is that if a robot is in SI, the other robot is either in mi or mi-1. And so here are the algorithm. So if the distance between the two robots seen by the robot executing the algorithm is in Si, regardless of the I stay stationary. If it's in mi with I even, then if I see myself on the left of the line, then I move to the other. If I see myself on the right, I do this little move here. And if the distance is in mi, so with I odd, then if I see myself on the left, I do this little move. And if I see myself on the right, I move to the other. What does it mean to do this small move? The distance here is actually chosen in a very particular way. The distance is such that if the other move like this and I move like this, the distance between the two robots after the move is such that I will enter in a configuration where the distance between the two robots is in Si with I even. Okay, so if both robots move like this, then I know that after that I will execute, I will be in Si with I even. And so the other must be either in Mi with I even or in Mi with I odd. And of course, we can see that if robots are stopped before they reach their target, for sure the robots will come closer. So at some point, the robot will be close enough so that they will always reach their target. So from now, we can assume that the robots will always reach their target. So how do we verify that this algorithm actually works? We start from, for instance, this configuration. This configuration represents a configuration where R1, which is the robot with the greatest level, is in Mi with I odd, and it sees itself on the right. So if you look at the algorithm, you say that in this configuration, I move to the other. The other robot sees itself on the left and is in Si with I odd. And if you look at the algorithm, in this case, we know that they don't move. So just by looking at where the robot sees the distance between them, we know what are the target. And by knowing the target, we know what will be the next configuration here. If a single robot is activated, for instance, just this robot, and the other stay idle, then the configuration will not change. If only this robot is activated, or if both robots are activated, the same will happen. This robot will gather with the other robot. So the next configuration will be the gathered configuration, and it's okay. The same will happen in this case. If R1 is on the left and is in Mi with I even, and the other robot is in S0, then after one round, the robots will gather. Now start with a little bit more complex configuration. Here we have R1, the first robot that is on the right and is in Mi with I even, and the other is stationary. So here it will move a little bit. So here we don't know exactly what will happen because the distance moved by the robot maybe is not enough to make them change their levels. So maybe we will end up in the same configuration again. But eventually when robots come closer, two cases can happen. Either the robot will enter in M0, so Mi with I even, and so in this case only one robot will move to the other and we reach the gather configuration, or this robot will stay in M0 and the other robot will leave the stationary interval and enter M0. In this case we have this configuration where both robots are in an M interval, and so if you look at the algorithm, they perform this kind of move, and here we know that either a single robot is activated. So if only this robot is activated, it's a gathered configuration, and it's not noted in this graph. If only this robot is activated, then we'll end up in this configuration eventually. Or if both robots are activated, we know that this distance here is exactly enough so that this robot will enter in the S0 configuration. So it ends up on the left and is in S0. And the other robot is now on the right. And if this robot is on S0, we have no choice. The other robot is in M1. And so we know that if starting from this, we can... so the numbers here are just the lemmas in the paper, if you want to look at the details. And here we just started from some configuration, but we can actually do this for all possible configuration. And starting from all the configuration, we can check that this graph is actually an acyclic directed graph. It means that there is no cycle, and eventually we will reach the gathered configuration, which is the only sync of this graph. And this is where if both robots have the same orientation. If they don't have the same orientation, we have another set of possible configurations. And again, we can check that this graph is acyclic and the only sync is the gathered configuration. So those graphs have been generated by a computer. We just proved every lemma that define all the transition, and we generated all the possible configuration and saw that we obtained this and there is no cycle. And the code of this program is available on Zenodo, and the link is in the paper. So we solved the rendezvous problem with no agreement on the axis direction and with a disagreement on the unit distance. And now the main question is, what if we do not have known bounds on ρ? So for instance, we just know that it's not 1, but it's arbitrary. So we conjecture that the problem is not solvable in this case, but we are not sure, so it's still open. So thank you for your attention, and I should be around to answer your questions. Thank you.